So now we're on question 7, which actually finally, after I've done everything, now we actually want to optimize over the value of t which we got. So first of all, let's just write out what we got in the previous step. We have expectation of, rather we have probability that s is greater than or equal to 1 plus alpha times mu is equal to probability that y is greater than or equal to e to the t times 1 plus alpha times mu. So t is greater than 0 is less than or equal to, I'm going to write it as e to the something this time. I wrote it as exponential of something last time, which is mu times e to the t minus 1 minus mu t times 1 plus alpha. And this is what we got in the previous part. So what we want to do is we want to minimize this with respect to t, because we want the closest or the smallest possible upper bound or the tightest possible upper bound. So we want to minimize this expression. So we want to minimize with respect to t expectation of mu e to the t minus 1 minus mu t 1 plus alpha. Now since the exponential function is monotonically increasing and the log of anything is monotonically increasing, the minimum of this particular thing is going to be the t which we get, which minimizes this particular thing, is going to be equal to, is going to be the same as minimizing the log of the same thing. So if we minimize the log of this, it's the same as minimizing this entire expression with respect to t, or the value of t which we get will be the same, which is log of that. I'm just going to not bother with the minor details of how this comes about because it's pretty obvious. Mu t times 1 plus alpha taking log. So how do we minimize this with respect to t? Let's differentiate it with respect to t. Let's call this g of t, right? So we want to minimize with respect to t g of t, which makes us take d over dt g of t, which is equal to, what is this equal to? Which is, let's take the first expression and we get mu times e to the t, and then let's take the second expression minus and differentiate the second expression. This is just using standard differentiation rules, and we get this. And we want to set this to 0 to find the extremum, to find an extrema, right? This implies e to the t minus 1 plus alpha whole times mu is equal to 0. And sorry, what am I doing? So this gets cancelled. So assuming that mu is not equal to 0, which means that p is not 0, assuming p is not 0 and mu is not equal to 0, we can just cancel this out, because mu will go down below 0, it's equal to 0 or mu, which is just 0. And we get e to the t is equal to 1 plus alpha, which implies t is equal to ln of 1 plus alpha. So this is the value of t which we get to minimize the entire equation. So this is g prime of t, right? To find, first of all, to find if it is, first of all, to find out that that it is a minimum, we need to check the second derivative, which is g double prime of t at t. We want to find out what g double prime of t is, because for a value to be a minimum, we need the second derivative to be positive, because the slope should be increasing at that point. So for this to be a minimum, we need d over dt of g prime of t to be greater than 0. Now let's just check that. So let's just differentiate this again. The second part is just a constant, so that goes to 0. And then mu times e to the t is again mu times e to the t. As we discussed, as long as t is a real number and mu is a positive number, e to the t is always going to be a positive number, and mu is always going to be positive if p is not 0. So this is greater than 0. Whoops, wow, this is really ugly. This is greater than 0, which implies that this t is a minimizer. So the minimum value, so t is equal to that gives us the minimizer. But we want to find the minimum value, right? Because we want to find, we want to plug in t into this equation to see what the minimum value is. Because a bound is not t, but a bound is a function of t, which is basically g of t. Right? So g of basically ln of 1 plus alpha is our bound, right? That is the best possible bound which we can get using this technique. Excuse me, which is equal to, I'm going to write exponential now because it's hard to write stuff on the numerator. Mu times, what is e to the t? E to the t, where t is ln of 1 plus alpha, is just 1 plus alpha minus 1 minus mu times 1 plus alpha, oops, not log, not 1 plus alpha, log of 1 plus alpha, alpha minus log of 1 plus alpha times 1 plus alpha, right? So this is, now I'll write this, 1 and 1 get cancelled, 1 and negative 1 get cancelled. This is e to the mu divided by, so you have e to the log of 1 plus alpha, sorry about that, log of 1 plus alpha whole to the mu times 1 plus alpha. What is e to the log of 1 plus alpha? This is just equal to 1 plus alpha, right? So it's e to the, oh, I forgot an alpha there. Mu alpha divided by 1 plus alpha to the mu times 1 plus alpha. So this is the bound which we get on the probability of s deviating by more than alpha times the mean from the mean. So this is what we got using. This is an approximation of Chernov's inequality because we used the approximation. I'm going to write it here. We use the approximation of 1 plus x. What was the approximation? We had, oops, I am blanking out. Okay, 1 plus x is less than or equal to e to the x. Oh, of course, yes. So this is the approximation which we used to bound using Chebyshev's Chernov's inequality. But the thing is that we don't need to use this approximation. We can actually get a stronger bound, which is done in note 19b. But with this approximation, this is the upper bound which we get on the probability above. And that's it for part 7.